Have you ever wondered why a rolling ball eventually stops, or how a massive ship can glide across the ocean? The answer lies in the work of Sir Isaac Newton and his three simple yet profound laws of motion. These laws get us a complete framework for understanding and predicting how any object will move or stay still when forces are applied. They connect the push or pull of a force directly to the object's mass and the resulting change in its movement. Newton's first law, often called the law of inertia, is simple but powerful. It states that an object will continue doing whatever it's doing, staying still or moving at a constant speed in a straight line, unless an unbalanced force interferes. Think about a hockey puck sliding across a perfectly smooth sheet of ice. If there were no friction or air resistance, that puck would just keep going forever. Inertia is the reason seatbelts are essential. Your body's inertia wants to keep moving forward even when the car has suddenly stopped. The first law helps us define two scenarios. If the forces acting on an object are balanced, equal in strength and opposite in direction, the net force is zero, and the object stays put or keeps moving steadily. But as soon as a friend joins your side in a tug of war, creating an unbalanced force, the rope accelerates or changes its motion. An unbalanced force is the sole requirement for any change in movement. We often use the term mass in everyday life, but in physics, mass is a direct measure of an object's inertia. The more stuff an object is made of, the greater its mass, and the harder it is to change its motion. Compare a large cruise ship to a small canoe. They might both be moving, but the ship has vastly more mass, and therefore vastly more inertia, making it incredibly difficult to slow down or turn, even with giant engines and rudders. Newton's second law is the heart of motion physics, summarized by the simple formula force equals mass times acceleration, F equals ma. This is our quantitative tool. It tells us that to accelerate a heavy object, a big M, you need a huge force, F. Conversely, if you apply a strong force, F, to a light object, small m, you get a huge change in motion, A. Let's look at the relationship between force and acceleration. Say you're bowling. If you push the ball lightly, it rolls slowly. If you use twice the effort, twice the force, the ball accelerates twice as much and rolls much faster. This is a direct relationship. Acceleration is proportional to the net force. If you want to change an object's speed or direction, you must change the magnitude or direction of the applied force. Now consider mass and acceleration. Imagine applying the same maximum effort, the same force, to throw a tennis ball and a shot put. The light tennis ball goes flying across the field, large acceleration. The heavy shot put barely moves, small acceleration. This is an inverse relationship. The greater the mass, the less the acceleration for a given force. Mass resists the force trying to change its motion. Because F equals ma is a math problem, we need units. Force is measured in newtons, N. This unit is based on the components of the formula. If you exert enough force to take a 1 kilogram object and make it speed up by 1 meter per second every second, you have applied 1 newton of force. This standardized unit allows scientists and engineers worldwide to communicate complex motion concepts clearly. The force of gravity provides a fantastic example of the second law. While all objects fall at the same rate in a vacuum, a heavier object still experiences a greater gravitational force. That force is what we call weight. Your weight is simply your mass multiplied by the Earth's constant acceleration due to gravity, which is 9.8 meters per second squared. That means a more massive person has more weight because gravity is pulling on their greater mass with a proportionally greater force. Not all forces are pushes or pulls that speed things up. Friction is the great opposer. It's a force that always acts in the opposite direction of motion or of the applied force, causing deceleration. It's the reason you have to keep pedaling a bike to maintain speed, and it's what converts kinetic energy into heat, like the heat on your tires after a long drive. If you want to calculate the net force, you must subtract the friction force from the applied force. Let's talk about falling. In a perfect airless world, a vacuum, a bowling ball and a feather would hit the ground at the exact same time. But on Earth, air resistance acts like fluid friction, pushing up against the falling object. When a skydiver jumps, they eventually stop accelerating and hit a fixed maximum speed, called terminal velocity. This happens because the upward force of air resistance has perfectly balanced the downward force of gravity, a real-world example of the first law creating constant velocity after an initial acceleration. What about something that's constantly changing direction, like a ball swinging on a string in a circle? Even if the speed is constant, the object is accelerating because its direction is always changing. And we know that acceleration requires an unbalanced force. This necessary force, which always pulls the object toward the center of the circle, is called the centripetal force. Without this center-seeking force, like the gravitational pull between the Earth and Moon, the object would simply fly off in a straight line, following the first law. Finally, we get to Newton's third law. For every action, there is an equal and opposite reaction. This law is often misunderstood because the forces involved do not cancel out. The key is that forces always come in pairs, and these forces always act on different objects. If you push on a wall, the wall pushes back on you. The action is on the wall, and the reaction is on you. Think about trying to move a very heavy, stuck object. The action is your push on the box. The reaction is the box's push back on you. The harder you push, the harder the box pushes back. If the reaction force on you is equal to the force you applied, why does the box ever move? Because the motion of the box is determined by the net force acting on the box itself, not the force acting on you. The third law explains everyday things like walking. When you walk, you don't push straight down. You angle your foot to push backward and slightly down on the ground. That's the action force. The ground, in turn, pushes forward and slightly up on your foot. It's that forward push from the ground, the reaction force, that actually propels you forward. Without that reaction, you'd slip and go nowhere, like on slick ice. This law is critical for all modes of transport. A car's tires push backward on the road, and the road pushes the car forward. Rockets provide the most dramatic example. The engine's action is pushing enormous amounts of hot gas out of the back. The gas's reaction is pushing the massive rocket forward with an equal and opposite force, creating the powerful thrust needed to escape Earth's gravity. To reiterate the critical point, the action and reaction forces do not cancel out because they are applied to different objects. If you push a book across a table, the action force of your hand on the book causes the book to accelerate. The reaction force of the book on your hand might make your hand feel sore, but it has no effect on the book's acceleration. Each object's motion is governed only by the net force acting on it. Let's summarize the three concepts quickly. Law 1 tells us that if nothing is happening, zero net force, nothing will change. Law 2 is the calculation. It shows exactly how much an object will change its motion when a force is applied. And Law 3 explains the origin of all forces. They always exist as two-way street pairs, acting between two different objects. Physics is all about prediction. If you want to know what a system is going to do, say a sled being pulled across the snow, you apply Newton's laws. First, you calculate the net force, applied pull minus friction and air resistance. Second, you use F equals ma to find the acceleration. Divide that net force by the mass of the sled. This allows you to predict exactly how fast the sled will be moving after a given time. These laws, first written down centuries ago, are the engine of modern life. They govern everything from the smallest collision of molecules to the orbital path of a satellite hundreds of miles above Earth. By grasping Newton's laws of motion, you're not just learning science. You are gaining the power to observe and predict the fundamental patterns of movement in the entire physical universe.